Hello, I'm Dora Blanco. I'm full professor at the University of Santiago de Compostela and senior researcher at CITIUS, also here at the University of Santiago. This podcast is on the School of High Performance and Disruptive Computing in Remote Sensing that has been held here at CITIUS during the first week of June 2024. This school has been organized by the Earth Science Informatics Committee of the IEEE GRSS Society. 35 students of all around the world has been selected to attend this school. This has been supported by different institutions, universities, and other companies. For example, IBM, NASA, ESA, Google Earth, the University of Iceland, the University of Boku, and other institutions, including, of course, the University of Santiago de Compostela, and in particular, CITIUS. The objective of the course is to provide to the students knowledge on the recent advancements, basically on high-performance computing, machine learning, and quantum computing applied to remote sensing. Quantum computing is an emerging paradigm that has been studied during this school. We have here two persons very closely involved in this topic. The first one is Dr. Gabriele Cavallaro. He comes from the University of Iceland and is also with the Jülich Supercomputing Center. The second one is Dr. Artur Miroszewski, that comes from the Jagiellonian University in Poland. I hope that you enjoy this talk. Hello, both.
Hi.
Thanks for being here. Welcome to Santiago. Thank you both for being here. We had different presentations on quantum computing during the school. As in previous editions of the school, you know Gabriele perfectly, as you are part of the organizing team of the school. The number of practical use cases in many areas, including remote sensing, require quantum computing algorithms, but many researchers do not know what is quantum computing and if quantum computing is a viable alternative for a researcher. For example, Artur, should it be possible to give a general informative idea of the quantum computing definition? What is quantum computing?
Thanks for the question. I will give a rather vague definition at the start that quantum computing deals with exploiting quantum mechanical laws for information processing. And this definition acquires more concrete meaning when we compare quantum computing with standard computing techniques that we call classical computing, obviously. Well, it might come as a surprise that both classical and quantum computers, they operate according to laws of quantum mechanics. But the important difference is in the scale of the system on which they operate on, okay? So the classical computer deals with hundreds, thousands, millions of electrons, and it's the collective behavior of the particles that we interpret in an informational way. And more or less, it agrees with our common intuition how those systems should behave. On the other hand, quantum computing deals with the behavior of individual particles. And this exact behavior diverges significantly from the collective behavior of standard computing. And the whole idea of quantum computing is to utilize this discrepancy between behaviors, maybe slightly non-intuitive behavior in the quantum case, for enhancing computational techniques.
And during this session of the course, we have talked about different problems to be executed on quantum computers. At this moment, the simulators of quantum computing is very developed. The computer is not as developed because in general they require a high power consumption, very, very high power consumption, but they are being used for executing algorithms, for example, of remote sensing and Earth observation, and what kind of problems are best suited to be executed on a quantum computer?
Well, first, I'd like to stress out that the problems that we can tackle with quantum computers and classical computers are basically the same problems, okay? But the huge difference is in the computational time. And we believe that some problems can be solved much faster on a quantum computer than on a classical computer, okay? So when you would like to find those problems that are well aligned with the quantum computational possibilities, we would first look at the problems which are hard to solve on a classical computer.
For example, deep learning neural network is a good option.
Yeah, well, I guess that it's quite computationally extensive task, right? So that's one of the tasks that are problematic for classical computers. Yes. Absolutely. But there are other examples, and in general, I would say that the algorithms which possess a vast computational, the solution space of those problems is huge. And we have some kind of a optimization or maybe combinatorial task. Those problems could be well suited for quantum computing, as we believe that quantum computing may be able to find those solutions faster than the classical computer. Okay.
So at the end, it's a way of saving computational time.
Yeah, I believe so. Exactly.
So it could be an advantage to take into consideration.
That's right. So in fact, we are talking about here quantum advantage, right, which should not be, confused with quantum supremacy, right? So as we know, we had some interesting news some years ago from Google, right, about quantum supremacy, but that was for a very specific problem, which is not, tractable by classical computers in, in a reasonable amount of time. While with quantum advantage, we are exactly looking for tackle problems that could be in Earth observation, remote sensing, but in many other applications like material science, so drug discovery, in which we aim at find the possibility to compute and to solve this issue on quantum computing in having the same, the size problem. Because at this moment in Earth observation in applications where we have big data, right? So we have a lot of big data. These data are not, we cannot handle this data on quantum computers yet, right? So that when we will be able to do that, we will achieve the possibility to have, an advantage in terms of usability. So quantum utilization is usability.
Yeah. It's clear, and it's very interesting because it opens the possibility to apply quantum computing to many fields that are not in our minds usually when we think on quantum computing, because the word quantum seems so complicated that immediately we have.
Yeah, indeed. This is fascinating where we're coming from, right? We're coming from a transformation. We started with analog computers, with moving objects, counting, and then we moved to the digital area where we finally got our transistors, right? So we're able to solve problems. I mean, starting from the war, but then having finally this computer solving applications that are important for our society. And finally arriving to quantum, right? So this quantum, which will be probably even a bigger, milestone or, step forward for our society. But, and always keeping in mind that these two, worlds will coexist together, right? So we're not going in a direction where quantum computing will substitute everything, right? This is, in my opinion, a domain in which we can solve some problems in a more efficient way.
like a coprocessor, like a GPU acting as a coprocessor, for example, because at this moment in all the supercomputers we have nodes with some of the nodes have 4 GPUs, for example, powerful GPUs acting as coprocessors.
Yeah.
Very well suited for deep learning problems, for machine learning problems, but not for all the problems.
Yeah, indeed. So Europe is, so being working in a supercomputing center, right? So we see quantum computing as an upcoming possible device which can be integrated in these systems, and this is what happened with GPUs, where GPUs at the beginning were mostly used for gaming.
Yeah, for fun.
Fun, right? But now they are used to basically train these foundation models, which actually can be used to really, simplify our lives. Just imagine our, speaker in the room, just asking questions.
And also can be lots of fun still.
Yeah, in a big number of directions.
Absolutely.
And you can ask questions about quantum computing to this device, and it will let you know. Or ChatGPT, for example, is this is like an area where computing is a very central role, right, in different applications. And it is fascinating the way are we heading, right? So now we are working with transistors that are getting below 10 nanometers. But the final aim is to have atoms, right? Atoms capable of handling information and to cooperate together in order to deal with bigger problems.
If I may add something, answering your question, I guess that it's worth stressing out that most of the computational tasks that we deal with are somehow complicated tasks, right? That consist of many subroutines that are to be computed. And how I see it, and I guess that Gabriele stated a very similar opinion on this topic, is that this coprocessor, the quantum processing unit, will be able to perform some subroutines, some subtasks, much faster than the classical computer, but still some tasks performed by a classical computer will be done faster. So I guess that this integration of both technologies for some tasks, well-optimized quantum computer for some tasks, well-optimized classical computer for some tasks, is actually the future. So using the, let's say, modular structure of the devices that we have available.
And exactly in this part, when you float, this computation in the quantum accelerator, this is where you can save energy, because you're not going to do it on a classical computer, which will consume more energy because it takes just more time. But you will just do it in an optimized way. But of course, optimizing these algorithms on these devices requires expertise, it requires knowledge, and that's also why it's important to make sure that that we can educate and we can, gather.
This is our task here at the school.
Absolutely. So would be very important to have people able to, let's say, passionate students that want to really take this challenge.
And to working in this area is one of the paths to the future. Lois Orosa, the director of CESGA, has talked during this school about the quantum computer that they have here at this campus at the University of Santiago, near the campus. And he has talked about different projects involving quantum computing, and we know that in Europe, in US, there are many invested in developing algorithms and developing architectures, more efficient architectures for quantum computing, trying to evolve in this area. I'm interested in now if there are libraries available with computing, with quantum computing algorithms, because in the case of, for example, GPUs, this was very relevant to develop the area. If the students or the young researchers, or the researchers in general, have libraries available, it's easier to go into this new world of quantum computing.
Yeah, so I think we should tackle this from two different perspectives. From the perspective of, let's say, an HPC center, which, who doesn't know yet what would be the winning quantum computing technology, right? So, and this is exactly what is now happening in Europe. EuroHPC joint undertaking, they're investing a lot of money to acquire different computers, different quantum computers based on different technology, and test them and and attach them, try to connect them to HPC system, and investigate which one are the one that can actually tackle some practical problems. So because at the end we are in a stage which is quite still early stage, right? In which we still don't know where all then this development in terms of software libraries will have to put their main effort. Nevertheless, it is true that nowadays it is very easy for students to access and to test algorithms on quantum computers because we have many libraries, right?
Yes, absolutely. Well, so when a student approaches the field of quantum mechanics, quantum computing, well, I guess that it can be slightly, maybe even intimidating at first, right? Especially as historically it was rather a domain of purely academic pursuit. But I guess that throughout the recent years, more and more entities, both public and private, got interested in utilization of quantum computing for various tasks. And that actually was able to incentivize a huge development also in the teaching resources. Okay, we need more people working in the field. And well, hence we need to give access to teaching resources. And you mentioned that we have some libraries, right? So apart from the libraries, usually there are also communities behind the libraries. And those communities not only prepare the software, but also lots of blog posts, articles, and basically manuals, hands-on tutorials for the students at home, being able to follow those resources and basically learn quantum computing on their own hand. Okay, so I guess that this field developed rapidly, and it's much more welcoming than it was a couple of years ago. And again, going back to libraries and the software, what is, I guess, important to stress out is that those software frameworks usually come with the quantum computer simulators. We already mentioned that word, and the huge advantage of using those software frameworks is that we do not have at start, when we start learning and just want to play a little bit with quantum computing. We don't have to book some computational time on a real quantum device, right? Yeah. But we can just play a little bit on the simulator, simulate how the quantum computer will behave on our local machine, for example, and then get a feeling how those things work. And maybe, hopefully, in the future, we'll be able to connect to connect to the real machine and do some impactful research, or maybe find some interesting use cases.
Thank you, and thanks for collaborating in the school, providing this information and this analysis and examples and use cases to our students. Thank you both for being here. Thank you very much.
Thank you very much.